Hi everyone. So last week we looked into linear regression and later generalized it to polynomial regression. So in other words, linear regression is a special case of polynomial regression. Now in this lecture we will look into a form of regularization called as ridge regression. I am Dr. Amrith Krishna and welcome to this lecture on ridge regression by egate.ai. So now let us look into the plot shown here. As we may see, the x-axis represents the predictor, which is the TV budget, and the y-axis represents the target variable or the sales that a company is expected to gain by marketing with the TV budget as shown in the x-axis. Now, those marked in the red are what we call as the training data points, and those marked in the gray are the test data points. So the legend is shown here. Remember, we can only use those in red, that is the training data points, to learn a function. So for a polynomial regression with degree equal to 1, which is nothing but the linear regression, what we can expect is to get a straight line. So a straight line, something like the one shown here. But as we can see, not all the training data points for this particular use case lie in a single line. So what should we do? So currently I am talking about polynomial regression, though what we have currently done is nothing but a linear regression where the polynomial degree is 1. So that itself indicates that we have higher degree of freedom, right? So I can probably select a polynomial regression with a higher degree. So let us say we take a polynomial regression with degree equal to 3. Now what we can learn here, the function that we can learn here, has become more expressive, or it has gone beyond what straight lines can essentially represent. So with a polynomial regression degree equal to 3, we may get a function as shown here. Now, the higher the degree of the polynomial that we are trying to learn with the polynomial regression, we end up with more degrees of freedom, which seems like a good thing. But we have to always keep in mind that we essentially are having more capacity to overfit the training data. So what does this overly fitting of the data mean? So if you look here, with a polynomial regression of degree 6, I am able to probably cover more data points. With 9, it increases. With 12, it further increases. But really, does it represent the true function that we want to learn? So what exactly does this overly fitting of the data mean? So overfitting is the phenomenon where the model is unnecessarily complex, in the sense that portions of the model captures the random noise in the observation rather than the relationship between the predictor and the target. So overfitting causes the model to lose the predictive power on new data. So in a more simpler term, the whole essence of learning a function by using those data points in red, which means the training data, is that it becomes useful in predicting unseen or for new inputs. And if that doesn't happen, if it just memorizes every data point in the training data without really understanding how exactly the function should look like, then it has no utility to us. So, in simpler words, a good way to identify overfitting is when the error on the training data is very low, which is generally seen to be desirable, but the error on new instances or the test instances is high. So let me write that here. So error on training data is low. Now this is a desirable feature. There is no doubt to that. The whole essence of training or learning a function using supervised approach typically centers around this idea that the training data error has to be as low as possible. But it is done with the intention on generalizing it to unseen data points or for data points which it has not seen during training. So in this case, let us say there is no data point for say 133. So we need to know for 133, it need not be 133, but let's say it's 113. Yeah, let's say for 113, what should be the corresponding y? So we have to predict that. Now, unfortunately, if our function doesn't do that, then this feature alone is not helping us. So even when you see that, you look into the learning process, you look into the training process, you calculate the loss, you have the cost function, and you find that the error, that is the predicted term for the training data point, and the true value, and if you take their difference, if that is sufficiently low, if it is really low, it's seen to be desirable, but only with a caveat that it becomes undesirable or it becomes overfitting when error on test instances is high. So this is the difference between generalization and memorization. So when you do overfitting, the system may predict very well on everything it has seen, but it doesn't do a good job at all for any new input. Now, why does overfitting happen? So primarily overfitting can happen either due to too many predictors or the coefficient values are too extreme. So predictors are the inputs that we decide upon, and the coefficients are the values that are learned via the function. So when we talk about predictors or the features, one possibility is that there are too many of them. We have considered too many of them and we don't have enough training data points to support those many predictors. So the feature space becomes high dimensional. Second thing is that we are making a model complex by having a high polynomial degree. So if the polynomial degree becomes high, there is too much degree of freedom for a system to learn different possible functions, and that makes it complex. A similar issue is that there are too many cross terms. So please remember, cross term mean those entries where you take the product of multiple features or multiple predictors. So when there are too many cross terms also, this system becomes complex. So a good indicator of overfitting is the low performance on test data in spite of having low error or a high performance on the training data. And in general, we may use multiple techniques in combination to prevent the overfitting. So a major aspect here is with respect to predictors is the model selection, which we will briefly touch upon for now. So model selection is the application of a principled method to determine the complexity of the model. So it may involve choosing the subset of predictors, choosing the degree of polynomial, etc. And of course, we need model selection to avoid overfitting. And another aspect which we didn't cover is that when the coefficient values are too extreme, that also leads to overfitting, which we will discuss now.